In this class, we're going to review the fundamentals of circular functions, starting with stuff like degrees and radians and how to convert between the two. Then we move on to some of the unit circle fundamentals and how we can actually use the unit circle to solve some circular functions. Enjoy. Let's make a start. So the agenda for this class is to basically go back to some of the review of circular functions, starting with the fundamentals. What is it about circular functions in the unit circle? How do we solve circular functions? That sort of thing. So let's take a look. Okay, so first thing we look at, degrees, radians, and the unit circle. The unit circle is something you'll become intimately familiar with as you do a lot more circular function stuff. I'll just pause for a second. Welcome, Sarah. There's a bunch of different cameras that are involved in the class, so just do a quick swipe between all of them to make sure you can see all those screen shares. If you have any issues, let me know, okay? And I'll help sort that out. But okay, so degrees, radians, unit circle. Unit circle, fundamentally, is just a circle centered at the origin with a radius of 1. So what's going on there is we'll eventually use that. A bit more complicated than just what's going on with these individual coordinates, but fundamentally we'll be using this for our circular functions understanding. Now, the reason why this matters, at least initially, is because it gives you the definition of how radians came to be. So you would have already been used to angles in terms of degrees. Radians is another type of way to represent angles. Specifically, you do it in terms of the circumference of a unit circle. So if you think about the circumference of any circle being 2 pi r, unit circle having a radius of 1 means the circumference of the unit circle would be 2 pi. That's why 2 pi would be 360 degrees, 1 revolution. That gives us a direct comparison between radians, so in terms of pi, and degrees, in terms of degrees, and so you can just rearrange this equation either side to get your conversion formula. You can go from one to the other using these two conversion formulas. If you want to get radians, you want to multiply by pi to put radians in it and divide by 180. Whereas if you want to go to degrees, you want to take pi out of it, so you want to divide by pi. So in the example we have here, 3 pi over 4 needs to go to degrees, so you're going to multiply by 180 and divide by pi. So you'll need to be at least somewhat familiar with your fraction arithmetic. Whenever you multiply two fractions together, it's just numerators multiply together and denominators multiply together. In the working out here, I've just cancelled the common factor of pi that's in the top and bottom. Factor in top, factor in bottom, they cancel out directly, and then you just simplify from there. Similar thing, 270 degrees to radians, so you're going to multiply by pi and divide by 180. So whenever you multiply whole number and fraction, that whole number multiplies your numerator. That gives you 270 pi over 180, which you can then simplify all the way down to 3 pi over 2. You'll also need to be familiar with your SOHCAHTOA, so the trig ratios, sine being opposite over hypotenuse, cos being adjacent over hypotenuse, and tan being opposite over adjacent. SOHCAHTOA is the acronym that allows you, or at least makes it a bit easier to memorize that. SOH, CAH, and TOA. The first letter is the trig ratio that you use, so S for sine, C for cos, T for tan, and the next two letters describe the division. So the OH means opposite over hypotenuse, AH means adjacent over hypotenuse, and OA would mean opposite over adjacent. So as far as solving those ratios, if you're told to solve sine, cos, tan, whatever, in this case we're trying to solve sine, we know that sine is always opposite over hypotenuse, as far as where those are located. So the opposite, well, I guess I'll go back here for it. Where those are located is always with respect to the angle itself. So if the angle is here, this angle that we care about, then the opposite to that angle is just the side that the angle does not intersect with. So the angle intersects this and it intersects this. The opposite must therefore be this side, the side that it doesn't touch. From there, the adjacent is going to be the side that the angle does touch, and the hypotenuse is just the longest side in your triangle. So that'll give you an idea of basically how to solve that. So if our theta is here, once again, this would be the opposite. This would be the hypotenuse. 2 divided by 4 gives you a half. Similar thing going on here, except in this case we're not trying to solve a trig ratio, we're trying to solve x specifically, where x is this length. We're given a known angle this time, 31 degrees, and we're given the hypotenuse. X is the adjacent in this case. We have adjacent, we have hypotenuse, we have adjacent. That means cosine theta is going to be the trig ratio that'll be useful for there. Theta is 31 degrees. The adjacent is x, the hypotenuse is 4, and so you would just rearrange that until you get the thing that you needed, which in this case was x. In Tech 3, that's as far as you go. In Tech Active, you could get that to some number of decimal places. Very unlikely that you'll need to, though. Usually they just want this answer. On the CAS, on the TI Inspire rather, you just want to click this button until it says degree, if you're working with degrees, or radians if you're working with radians. And on the Casio, it's down here. If there's any questions at any point, feel free to let me know, either by hopping off mute or like raising a hand, hopping on chat, any of those. In this case, we have the same triangle, but we're not looking for sine theta or any like specific thing like that. We're looking for theta itself, not the ratio. So we're still going to start off with our sine theta equals 2 over 4, just like we did before. But we need to figure out a way to get theta on its own. That's where the inverse trig functions come into play. So basically what's happening here is we have this equation that says sine theta is equal to a half. What's going on to get us from this equation to the sine inverse? I'll write on the handwritten bit. So we have sine theta equals a half. This is what actually happens when you take the sine inverse of something. Just like how, if you've done it yet, you'll have like, you can wrap things in logarithms, you can do composite functions, that sort of stuff. You can actually wrap both sides of this equation with the sine inverse. So what this would look like is, I'll even do it in red. So you'd have sine inverse of sine theta equals sine inverse of a half. Right, you're wrapping both sides of the equation with the sine inverse. Now, there's this property that will be useful when you do your inverse functions, when you revise that or learn that for the first time, which is that anytime you have f inverse of f, that always just equals x, or more specifically, whatever's in the brackets of this one here. Which is why when we do sine inverse of both sides, sine inverse of sine just gives us theta. And then this just stays as it is. So that gives us theta equals sine inverse of a half, which some of you may already know. That just means, so where's sine a half? Sine is a half at the pi over 6 angle. Now, that's just me remembering the unit circle. We'll look at that in a bit more detail if we need to. Okay, so for now you could leave it a sine inverse of a half if you don't already know how to get to pi over 6. Otherwise, the CAS could also potentially help there. And I have that in the screen share as well. So you can evaluate that on the CAS like this, or you could even, in a separate way, use a solve function. You could just say, where does sine equal a half? And as long as you put a domain associated with that, you'll also get that angle that's necessary there. Same thing with the Casio. That's it for fundamentals there. So if there's anything you'd like me to clarify further, please let me know. Otherwise, we move on to some slightly more detailed stuff on the unit circle. I'll just take a quick pause for that. Okay, so more unit circle stuff. More specifically, instead of just having a unit circle that's centered on the origin that has a radius of 1, we now want to care about the coordinates that are somewhere in between all those intercepts. Now, what we find is that any coordinate on the circumference on the unit circle, the x-coordinate is always given by cosine of theta, and the y-coordinate is always given by sine of theta. Now, here's the reason why. If I were to draw a straight line connecting the origin to some point on the circumference, we could create a triangle from that, right? It's going to go some horizontal distance and some vertical distance. If you were to look at this triangle specifically, theta is always with respect to the origin. This hypotenuse is always 1 because it's a unit circle. This hypotenuse, the line that connects the origin to the circumference, has to have a radius of 1. That's what makes it the unit circle. So hypotenuse being 1 here, this is our adjacent side because it's the side that intersects the angle, and this is the opposite side since it's the side that does not get intersected. If we consider our trig ratio sine and cos being opposite and adjacent over hypotenuse respectively, when hypotenuse is 1, they just simplify down to just opposite and adjacent. So in that way, the opposite is therefore sine theta, the adjacent is therefore cos theta. And if you look at what that actually means, if cos theta is just the horizontal distance here, well, horizontal is just x. And so under those circumstances, cosine theta is your x-coordinate. For that exact same logic, sine theta becomes your y-coordinate. This vertical distance is just some vertical distance as far as y is concerned. And so that gives you your y-coordinate. So that's a bit of a refresher as to why the x is the cos and sine is the y as far as coordinates go. It's probably also worth pointing out that there's also this idea that tan theta gives you gradient, and it's based on this as well, which is if you imagine doing the rise over run of this, well, the origin being one of those points means you just do y divided by x at that point. And so if you do y divided by x, that would be sine divided by cos to get your gradient. And if you know that tan is equal to sine divided by cos, then that therefore means that tan theta must be the gradient. So that's where that comes from. So basically, if you know the angle that your line makes, so there was a 31 degree or something like that in the previous one. If you know that your line makes an angle of 31 degrees, then tan of 31 gives you that gradient. A little bit nuanced. This picture is a bit off for that. You'd have to have the 31 degrees on this side instead, but we'll see in a bit more detail the semantics around that. Okay, so some initial exact values of the unit circle. First things first, we look at the quadrant boundaries. So just like an XY axis has quadrants, so too does the unit circle, because the unit circle does exist on the XY axes. Quadrant 1, 2, 3, and 4 exist the exact same way that they have always done on the XY axes, the Cartesian plane. The fact that the radius is 1 means that all the, now I say corners of the circle, even though they don't quite have corners, we'll say boundaries, I guess. All these boundaries are therefore going to have coordinates of 1 and 0 or -1 and 0 respectively, because if you draw any straight line from the middle, well, it's going to have a length of 1. We also typically write everything in terms of radians at this point. Very rare that you'll have to do anything with degrees related. So we give this as 2 pi or 0 radians because both of those imply either the starting point or they imply that you've done a full revolution. Remember, full revolution being done in 2 pi. Then if you imagine halfway, so half a revolution would therefore be pi, half of that, so quarter revolution would therefore be pi over 2, and all you would do there is backfill because you realize that everything is separated by pi over 2 here. 0, pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and that would continue on and on. As far as sine, cos, and tan for those angles, Well, if you remember that cos is the x and the sine is the y, then literally all you're doing is looking at the xy coordinates and then plugging those into your sine or cos. So if we look at the 0 or 2 pi spot, if you look at the y value there, that's 0, so sine is 0. If you look at the x value here, being 1, that means cos is going to be 1. As for tan, you just do the division of those two things. You do the y divided by the x, 0 divided by 1 is 0. That'll also explain why tan has some undefined spots. Because if you look at the pi over 2 spot, you'll notice that you do 1 divided by 0, which undefined. So you would just do that. You just do that for all the spots on the unit circle, all those quadrant boundaries. So those are the quadrant boundaries. You'll also have to eventually know, if you don't already, the interquadrant angles. Now, when I say you'll have to know them, I mean you'll have to have them memorized. These do not, unfortunately, appear on your formula sheet. And so this is something you do have to practice many, many times of redrawing the table or redrawing the unit circle, however you do it. You just need to make sure you've got them memorized. So those are pi over 6, pi over 4, and pi over 3. And you need to know the exact values of a half, root 2 over 2, and root 3 over 2. That's kind of the bare minimum when it comes to memorizing. Everything else in the table or in the unit circle can be derived from just knowing those 3 angles and these 3 exact values. So if you want to absolutely minimize the amount of work that you do, those will be the ones that you memorize. This is what the completed unit circle looks like. So you'll notice the quadrant boundaries from before, but you'll also notice that you now have these pi over 6, pi over 4, and pi over 3 type angles. And you'll also notice the exact values, root 3 over 2, root 2 over 2, and a half. As far as how to now memorize this whole thing, my recommendation is focus all your effort on this first quadrant, and then you can flip things around. Well, first we'll look at how could you do this first quadrant. This whole first quadrant here is described by this table up here. Here's how it works. First things first, you're just going to write the angles in order of ascending order. Right? It should be fairly trivial to understand that pi over 6 is a smaller value than pi over 4, is a smaller value than pi over 3. You're going to write them in ascending order. From there, the order in which you write these coordinates will depend on if x is getting bigger or smaller versus if y is getting bigger or smaller. Reminder, x is cos, sine is y. So if you look at these spots on the unit circle, they change their x and y values depending on how far up or down the unit circle they go. So if we look at this spot here, for example, we notice it has a height of there, roughly speaking. Versus if we look at this spot, it's above. So effectively what we're saying is, as our angle gets steeper, the y values should get bigger. So what you do is, you take the 3 values that you know, the half, the root 2 over 2, and the root 3 over 2, and you write them in ascending order. So you take that half, root 2 over 2, root 3 over 2, you write those in ascending order. From there, you could apply the exact same logic to the x if you like, or you just invert it. So the x value, if you look vertically, like where it touches the x-axis, you can see that as I get higher up the unit circle, the point where this line touches the x-axis gets closer to 0 every single time. It gets closer and closer to 0. So we start with our biggest value and we work all the way down to our smallest value. So whichever one of those makes more sense to you to start with, by all means use that. Then you can either invert it to get the other one, so just do the reverse order, or you could use that same logic, up to you. That gives you a way to fully fill out that first quadrant. So hopefully not as bad as it looks. I know there's degrees angles in here. It's basically never come up. It's very rare for degrees to ever show up at all, so when you're memorizing this, focus the bulk of your time on understanding the radians versions of these, and once you got those down, then you can start worrying about what the degree equivalents are. By far, we do a lot more work in radians than we do in degrees. But okay, that gives us our first quadrant. From here on out, there's a few symmetry properties to be considered. The first is that every single quadrant on this circle has some kind of pi over 6 angle on it, some kind of pi over 4 angle on it, and some kind of pi over 3 angle on it. That's the first thing to recognize. That thing is that the coordinates at those spots are just reflections of the coordinates that existed on the first quadrant. So if we consider this pi over 3 angle and this pi over 3 type angle, you'll notice that the coordinates are identical with one exception, the negative on the half. How you identify whether you have a negative or a positive simply depends on what quadrant it's left in. Reminder that these are xy pairs. So essentially, if you're on the left side of your y-axis, all those x values should be negative. Right? Anything on the left is always a negative x, which is why you'll notice there's a negative on all of these. Also, anything below the x-axis should have a negative on the y, since that's where negative y values go, which is why, again, there's going to be a bunch of negatives here, here. All these y values are going to have negatives on them. So, all you've got to do is identify, do I have a pi over 4, pi over 6, or pi over 3 type angle? If so, use this exact coordinate you already know, flip over to that spot, and just chuck negatives on it depending on what quadrant it's in. That's all that ends up being. So that gives you a much nicer way of getting all of these coordinates, or at least getting the coordinate that you need for a given point in time. As far as how to get the actual number here, yeah, sure, it's a pi over 3 angle, but what number goes in the numerator? That you literally just count. So pi over 3 means that for a semicircle, you've cut that thing into 3 spots. A semicircle is from 0 to pi, so pi over 3 means you've cut it in 3s. So 1 pi over 3, 2 pi over 3, 3 pi over 3. Then you just do that again. 4 pi over 3, 5 pi over 3, 6 pi over 3. You're just counting around the unit circle. Pi over 4 means cut your semicircle into 4 bits. Pi over 6 means cut your semicircle into 6 bits. So that'll give you a nice way to get those angles as well. So all in all, fundamentally, as long as you know pi over 6, pi over 4, pi over 3, and then these exact values, half, root 2 over 2, and root 3 over 2, with a bit of logic, you can flip things around as you see fit. Don't have to memorize every single point on this unit circle. Okay. Alright, by the way, these are recorded, so you can check those if you want to see how I describe that again. I even have it written out, although I'm not super proud of how this is written out. It's kind of hard to describe that without using words. So if you like written, by all means use that, but otherwise I'd say just stick with the recording. Now, one of the kind of issues here is that this gives you sine and cos, nice and easy. What about tan? You've got a couple of options when it comes to tan. Either do the exact same thing I just mentioned, but for all the tan values. So those tan values have the same angles of pi over 6, pi over 4, pi over 3, but they come with a few new exact values. Those being root 3, 1, and either root 3 on 3 like I've written here, or 1 on root 3. Those are both the same fraction. So you can either memorize those, which can be handy, but just speaking from experience, when I was doing this in year 12, I actually did not memorize my tan values. What I did instead was I knew that tan was always sine divided by cos. So I know, let's say for example the pi over 6 one. I know that sine is a half, I know that cos is root 3 over 2. If I do sine divided by cos and simplify that fraction, I get that 1 over root 3 angle, like I mentioned. Same thing over here, these go to 1. Same thing over here, these go to root 3. That's just what I did. I don't know if I necessarily recommend it. I'm just giving you those are the two options. Either memorize 3 new exact values, or just do this calculation anytime you want to get your tan values. Yeah, that's that. We'll worry about negative angles in a bit. In fact, yeah, I'll briefly talk about what that is. So negative angles simply just means instead of going in a counterclockwise direction, you go in a clockwise direction. So now pi over 6 is bottom, then pi over 4, then pi over 3. But you're just going to put a negative on all of those. It's just the going in the reverse direction. That's all I'll say about that for now. Anything to clarify about that, please let me know. Otherwise, we move into the last docket for this one, which is how to actually use that unit circle for anything useful. So let's take a quick pause for that. Okay, so we're going to do what's called evaluating a circular function. Now, that's slightly different to solving a circular function. What I mean specifically is that evaluating a circular function means you have the angle, but you don't know the exact value. So in this case, it's like, okay, what is sine of 3 pi over 2? We have the angle, we just don't know what that equals. First step, just find that angle on your unit circle. You either have this memorized in your head, or while you're still learning it to start with, you refer to either my notes, or maybe you've got one in your own bound reference somewhere. That's going to be this spot here, 3 pi over 2, and it corresponds to the coordinate 0, negative 1. Next up, you either give the x or the y coordinate, depending on if you have sine or cos. Remember, sine is the y, cos is the x. So if you want to do sine of 3 pi over 2, we give the y value, so negative 1. That's all that is. You'll come across a case where your angles will be larger than 1 revolution. So if you try to look on your unit circle for where 7 pi over 3 is, you're just not going to find it, right? The last pi over 3 angle caps out at 5 pi over 3, technically 6 pi over 3, if you want to think about it. So you've got to imagine how we're gonna work that out. There's two ways you could do it. If it's a small enough angle, you can just keep counting. So you can do pi over 3, 2 pi over 3, 3, 4, 5, 6, and then 7. If you just keep counting around the unit circle, you'll get there. Now, don't do that for massive numbers, that'll be kind of a headache, but if it's small enough, then by all means, just keep counting around, and you'll get to the equivalent spot. So basically this is saying that 7 pi over 3 is functionally the same as pi over 3. And so under those circumstances, you look at the pi over 3 angle and its coordinate there. I still haven't fixed the notes on this one yet. It was cos, but I highlighted the y value. I wrote the correct thing, though, which is cos, you do the x, which should be a half. Just ignore that that's highlighted still. Okay. Now, if you have 55 pi over 6, not super effective to do that, right? Like, feel free to count that many times, but that's a lot of time. So, my recommendation, split it up into a mixed fraction. Get the whole number portion of it, get the fractional portion of it. This is literally just doing 55 divided by 6 like you would have done in, I don't know, year 6 maybe, a long division kind of thing. Point being is that it fits 9 times with one remainder, which is why we have 9 pi and pi over 6 as the remainder bit. Now, here's the hack. This integer value of pi tells you where to start on the unit circle. Odds are always on the left, evens are always on the right. The reason why, if you imagine counting in terms of pi around the unit circle, you start at 0, this would be pi, half a circle, this would be 2 pi, a full circle, and then from there you just keep going. 3 pi, 4 pi, 5 pi, 6 pi. You'll notice that all the evens are on the right, all the odds are on the left. So this 9 pi here tells you immediately we're starting on the left. This remainder of pi over 6 tells you we're starting at, well, it tells you to then go a further pi over 6 from that starting location. So you just go to the pi over 6 angle that exists on your unit circle, and then you give the coordinate, what is it, cos, so we give the x coordinate there. So in that case, negative root 3 over 2. as said here. That's that one. Negative angles. I mentioned this one before, which was that negative angles just mean you're going backwards around the unit circle. That's what's actually happening, although I find a better way of solving negative angles is to actually first start by ignoring that a negative angle is even there. First step is literally just strip the negative of it and just say, where is 7 pi over 6 on my unit circle? A lot easier. That's going to be this spot here. Now, what is effectively happening by putting a negative there is a flip vertically. And so all you do is you say, okay, I'm at the pi over 6 spot on this angle, on this quadrant rather. Flipping vertically means putting myself at the pi over 6 angle on this quadrant. So we can solve negative angles in 2 steps, like that. Strip the negative, flip vertically, now that's the coordinate you care about. We had sine, so we give the y value, which is a half.
Chris,
Yo.
if we just count clockwise, would it be the same thing?
Yeah. So here's pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5, 6, 7 pi over 6, which is counting backwards there. The reason why I say that is because when you have like negative 77 pi on 6, it's like, okay, I can split that into a fraction, but when there's a negative on it, it makes it a bit weirder. It doesn't actually change anything, but it just feels weirder to me.
Yeah.
So it's really, yeah, it's up to you which way you want to go about it. The only thing I was trying to cover there was like, this would now have 2 negative numbers, which if you are inclined on doing that, a negative on this doesn't actually do anything because pi is still there, negative pi is still there. And then negative pi over 6 just means going backwards that way if you had to do that. So up to you if you want to do it that way, by all means. I just like to do this because at least you're using things that are already on the unit circle. Personal preference. But good point bringing that up. Okay, so those are all little hacks that I've got there for that. That does pretty much conclude the lecture portion of this. So if there's any further questions, please let me know. And if there's anything you want to specifically have a look at from this, we can do that. Otherwise, I personally find that most students struggle with like this stuff, the actual evaluating side of things. So I'll focus on that unless anyone wants me to do otherwise. So I'll pause for a bit while you think if you have a question. I'll do some screenshots so you can use the unit circle should you need it. I'll even grab a copy of the negative angle unit circle if you like counting backwards as well. You can see which ones I made myself or which ones I just copied from the internet somewhere. Okay, cool. Let's do some evaluating. Oh yeah, okay, they do split it up into 2 separate bits, don't they? Yeah, okay. Cool. Alright, so we'll do some stuff in 14b. I'll give you some screenshots if you need to refer to the unit circle there. For the bulk of this now, we're going to go through the handwritten bit. So I'm just going to turn the phone back on. And I'll start writing some out. So, yeah, I'll kind of just use this as a guideline, really. So I'll just chuck some out. So if we wanted to do sine of pi over 2, what's going on there?
We locate sine pi over 2. We just locate pi over 2 on the unit circle.
Yep. So,
And I think the coordinate is 0, comma 1 by memory.
yep, 0, 1 is
And
correct.
since the sine value is always a y value for the coordinate, sine pi over 2 will just equal to 1.
Correct. Yeah. So you can use a copy of a unit circle you have if you need it. All this is correct. The 0, 1 is the coordinate up here at pi over 2. And because the y value is sine pi over 2, the y value is sine, then yes, you give the 1. Sweet, crushed it. All right, next one up. Cos of, let's say, pi. Another one of those not interquadrant, the quadrant angles. What's going on at cos of pi? Cos of pi -1. Yep, so the reason why -1 is because pi is over here. The coordinate at that spot is -1, 0. Cos being the x, you give -1. Nice. Thanks, Pierre. Let's do something a little bit slightly more challenging. We'll do an angle that doesn't quite exist on the unit circle. So let's go with the 7 pi over 2 one, because why not? Let's make it cos of... No, I don't want to do cos, we'll do sine. Otherwise you can cheat. Sine of 7 pi on 2. How's that all about?
Chris, is this one again?
Is it 1? I think it's -1. I'm kind of just eyeballing that though. Let me think. 6, 3. Yeah, this one's going
Because
to
I
be
thought
negative.
we would have 3 revolutions of the circle, and then we just go back to pi over 2.
Not 3 revolutions, 3 half revolutions. So it's 3 pi, right? Is it because did you split it up into 3 pi and pi over 2?
Yeah, yeah.
Yeah, so this 3 pi doesn't mean 3 revolutions. That actually means 1.5, because remember, 1 full revolution is 2 pi. The way I think about it is odds are on left and evens are on right. So this odd means that you're at the left-hand side part here, and then another pi over 2 means you go down to here. Okay? So yeah, all that was happening there was we take the 7 pi over 2, we split it up into a whole number and a fractional value. 2 goes into 7 3 times with 1 remainder. Odd means left, and then pi over 2, you just continue on there. So with that in mind, the fact that we're at this spot on the unit circle, what does that make our sine? -1, yeah, correct. Thank you. Awesome. All right. Now, just for fun there, yeah, I mean, it kind of, I'll do a different angle, but the reason why I split up cos, so let's do cos, I'm just going to go weird with it. Let's go 55 pi over 2. I haven't really talked about how to quickly find this one. Well, I've taught you how to do it quicker, but there is a quickest way for this. Curious if someone has an idea.
Is this just 0?
It is just 0, yeah. Now I'm curious to hear what method you used. Hello?
I just like thought that 55 pi over 2 is pretty close to 56 pi over 2.
Yep,
And then that would just be 14 revolutions of the unit circle.
sure.
But since we're pi over 2 away, I just went down. I just went back pi over 2 and then look at the cos coordinate there.
Yeah, brilliant. I actually love that a lot. That's different to what I was thinking, but that's also good because 56 pi over 2, yeah, that simplifies down. Cool. Yeah, I like that. What I was thinking of is it actually doesn't matter what type of pi over 2 it is, whether it's up here or down here. Both of them have an x coordinate of 0. And so as soon as you see a pi over 2 type angle that can't be like you got odd over 2, that can't be simplified, right? doesn't actually matter where it ends up there. You just go straight for 0, and it doesn't matter which one it was. So there's a similar thing for sine. Like if I do sine of 1000 pi, right? Similar thing going on there. What's that going to equal? 0. Yeah, thanks, Pierre. So 0 because doesn't matter what integer value of pi you're at, you're always horizontal, which always has a y value of 0. So there's another little hack for you if you get those quadrant boundary angles. That's pretty much it there. I mean, you can even see in the book they've got some nasty ones there, like 211 pi and 57 pi, and what's the worst? Yeah, stuff like that. Okay, that's about it for those that I wanted to have a look at. Oh, actually, no, there should be a negative one. Yeah, let's try a negative. Cool, I'll make up a negative one. Let's go for sine negative 3 pi on 2. Yeah, correct, Pierre. One's correct. Reason why, for everyone else, is a couple ways you could do it. You either just count backwards by pi over 2's, so 0, pi over 2, 2 pi over 2, 3 pi over 2. That puts you up here, which is going to be the y-coordinate of 1. Or you do what I mentioned at the beginning, which was you ignore the negative, 3 pi over 2 is here, and then you flip it vertically to get that. Either of those works fine, depending on what your preference is. Cool. All right, that's that one. Oh wait, they gave tan its own special thing. That's kind of funny. Tan also has a few hacks to it. Yeah. In fact, literally all the examples I give in this one is going to have has a hack for tan. So let's have a look. I'll just give, I don't know, let's say tan 3 pi.
Is it just 0?
It is just 0, yeah. I can imagine a few ways you could do it. What was your idea?
So you know how like you were showing us that any pi value for sine will equal 0, like when
Yep,
it's just pi.
yep,
So then since tan is a sine over cos, any if you divide 0 by anything, it's still gonna equal 0. So
mhm,
that's
exactly.
why I thought tan 3 pi would be equal to 0.
Yeah, no, that's perfect. Love that. Yeah, it's exactly what I was thinking there. Nice. Um, that's going to be that one. And then lastly, go tan of 101 on 2. Tan 101 pi on 2.
Undefined.
Undefined. Yeah. What's going on there?
Um, I already know like from the graph, like the tan graph, that pi over 2 is an asymptote, but
Hmm.
also you know how we were talking about that any like if you see pi over 2, cos will always equal to 0, and since tan is sine over cos, we'll have a divide by 0 error.
Precisely. Yep. There you go. So the tan quadrant boundaries are super chill. It's either 0 or undefined. I mean, to be fair, the same thing can be said about sine and cos being 0, 1, or well, I guess there's 3 versus 2. Slightly easier, let's say. Um, yeah, that's all that is. Nice. Yeah, I mean, it does hit all of those. Interquadrant angles, sure. Let's skip over all these. Yeah, okay. Is there any good ones? Yeah, I guess at a certain point, once you've got the unit circle in your head, it's all just kind of like the same. So these will be the interquadrants specifically. So no more boundaries anymore, a fair few more things to look at. Let's go sine of 2 pi on 3.
Is it root 3 over 2?
Root 3 over 2 sounds pretty good to me. Why is it root 3 over 2? Well, like that's
Um,
kind of a tough question to ask.
I'm pretty sure it's because from what I remember, the interquadrant angle
Yeah,
of pi over 3 is 1 over, like the coordinate is like a 1 over 2 and root 3 over 2.
yeah.
And so since 2 pi over 3 would go into the top left quadrant
Hmm.
of the unit circle, um, we know that only the x coordinate is changing, but since we're trying to find sine, that doesn't really matter. So sine will just remain root 3 over 2.
Correct. Yeah. So as you were saying, half comma root 3 over 2 here, and if you flip that over, only the x would get the negative. So this would be like a little excerpt from the unit circle you've got in the screenshots, should you need it. Yeah. So final answer, root 3 on 2. Nice. All right. We'll do one cos. We'll do a tan, and maybe chuck a negative angle in there. Let's see. How about cos 7 pi on 4? Root 2 on 2 is correct, Peel. Yeah, nice. Um, do you want to give a shot at explaining it? I know you're currently typing everything out. It's probably a bit hard to explain by text. Maybe just a quick yes or no. I'll explain it, or you can explain it. Yeah, okay, you just looked at the diagram. Yeah, that's fair. So on the unit circle, if you're just looking at diagram, obviously, so 7 pi over 4 is going to be this coordinate on the screen share. And so giving the x there because of cos positive root 2 on 2. Yep. Sweet. All right. And then last up, we'll do tan of, yeah, 11 pi on 6. We'll do that tan one.
Is it negative? Hold on. Is it just negative root 3?
Negative root 3, I believe, would be the pi over 3 version. Um, when you did when you got that answer, was that like a memory thing, or are you doing sine divided by cos?
I think I just I tried to find the sign code like the coordinate fully and then
Yep.
divide it, but maybe I got the wrong coordinate. I'm not sure.
Yeah, I mean, I'll double check just to make sure I didn't brain fart there. Um, yeah, no. So it should be negative root 3 on 3. The reason why, if you're going to do your If you want to do your sine divided by cos, what did you have as a coordinate for 11 pi on 6?
I had root 3 over 2 and -1 over 2, which I'm not sure if that's right.
No, that's fine. Root 3 over 2 for x, because it's the furthest x, and negative a half. Yeah, that's good. So sine divided by cos means you're doing negative a half divided by root 3 over 2. So that'll be the first thing I ask, which is, did you have that the right way around?
I think I divided, I put the root 3 over 2 first,
Yeah,
and that's probably what happened when I was flipping fractions.
correct. Yeah, sounds good to me. Well, sounds like what's happened. So yeah, for everyone else, when you have this division here, you flip to a multiplication, 2 over root 3. The 2 being in the top and bottom will cancel, leaving you with -1 on root 3, and that is a perfectly valid answer for tan. Now, just as a fun bonus here, the question is now, why is it that I've got negative root 3 on 3 written? I did say those were equivalent values. In what way can I prove they're equivalent? So I guess I'll put it all on the same page, which is, why is this equal to this?
Did you rationalize it?
Rationalized it. Yeah, correct. So how does that actually look? So let's say I wanted to go from here to here. What do I actually do to this left-hand side to make it look like the right-hand side?
You multiply by root 3 over root 3.
Absolutely. Yeah. So you got the -1 over root 3 from before, multiply by root 3 on root 3. That's the same as multiplying by 1. And then, well, you're going to get negative root 3 on top, and then root 3 on root 3 times root 3. Those roots cancel down to just giving 3. Um, yeah, that's all that is. And it does the exact same thing if you wanted to go from right to left as well. You do the exact same multiplication, but that'll put it in the bottom instead of the top. Sweet. Okay, that's that one. And I guess we'll chuck in a negative angle. Let's see. Yeah, here's a fun one. Cos of negative 21 pi over 3. Let's try that. Cos negative 21 pi on 3. Where did we end up? Oh, that's a poor one. Oh well. It's a cheeky question.
Chris, is it -1?
It is -1, yeah. Despite the fact that it appears like a pi over 3 angle. Why have we got -1 as an answer?
So first I simplify that to -7 pi.
Yeah, it's got a denominator of 3 there, but that doesn't mean it wasn't actually simplifiable to a to a whole number there. Yeah.
And obviously, like, if you use like your method, like just like disregard the negative, you go when if we go to where -7 pi is, it's just on the left side where pi usually is on the unit circle.
Mhm.
And even if we're gonna flip vertically, you can't, so it just stays there.
Correct. Yeah, flipping vertically, there's nowhere to go. It's tangent, and so unless you're shooting off into space, there's nowhere to go. Yeah. Um, so basically, any plus minus whole number of pi always sticks at the horizontal line. Nothing ever changes there. Yeah, cheeky one, that one. Yeah, that's probably about as unique as that's gonna get. Haven't got any. I guess I'll briefly just touch on one thing that I saw as I was scrolling through here, which is very much an engineering thing. I probably had the exact same rant last time we looked at this, but they've got this little section in the book which is approximating sine theta for small theta. Um, it kind of became a meme in engineering, as far as funny as math memes can get, I suppose. But effectively, all it's trying to do is tell you if your angle is sufficiently small, um, that the sine of that angle is pretty much the same thing as that angle. So if I just pull up the CAS for a second, and I do like sine of, like the very basic one is sine of 0 is 0, yeah? Perfect one-to-one match. The angle and the value are the same. If I go a little bit bigger, sine of 0.01, I get approximately 0.01. If I did sine of 0.1, it's, still there to two decimal places, but it's getting a bit further. Then if I do sine of 1, it starts to get a bit further and further away from being accurate. I don't know why it's there. It's really an engineering thing. It's a useful engineering thing, but not a not really something you should need to know in methods. Although it'll be really funny if that shows up on an exam, because then you'll be prepared for it. Cool. That's about it, really. I know I got a couple minutes left, so I'll stick around if you have anything you'd like to clarify. But I've pretty much hit all the unique ones. I know I didn't really touch the degrees yet. Um, yeah, maybe that's what I'll do for the last 2 minutes. Um, yeah, so you've got your radians, which is by far the most important part, the pi over 6, pi over 4, pi over 3. Everything that I talked about as far as memorizing your unit circle can also apply to the degrees versions, as far as as long as you know the degrees of 30 degrees, 45 degrees, and 60 degrees, as long as you know those are pi over 6, pi over 4, and pi over 3, from there you just do that counting method all the way around. So 30, 60, 90, 120, 150, 180, it's probably a bit more intuitive that there's 360 degrees in a circle. So counting around should almost be a little bit easier because you learn degrees a lot earlier than you learn radians. So basically, even when I get a degrees question, which is very rare, the first thing I'll do in my mind is convert it to radians. So even that, right? Maybe you don't even bother memorizing any of these degree angles that are corresponding to radians, and you literally just do your conversion from degrees to radians by multiplying by pi, divide by 180, and then it's just what you're already used to. So that's another way of going about it. That'll minimize what you have to memorize. Cool. All right. That's about it from me. I'll stick around for a little bit if you want me to clarify anything. Otherwise, take care.